Welcome to week 11 of the NPTEL session on C programming. Today we will be covering mainly topics related to numerical interpolation, integration, and ODE solving. Specifically, we will be covering Lagrange interpolation and in terms of interpolating algorithms. In terms of integrations, we will be covering the trapezoidal rule for integration, and then we will be covering the Runge-Kutta method for differential equations. And if you recall, in the previous week we talked about root finding using Newton-Raphson and using the bisection method. So in the similar spirit, this builds on those previous concepts and also looks at different other numerical techniques. And so let's get started. So let me start by sharing my screen. I hope all of you can see my screen. So I'll first discuss the MCQs from previous year assignments, and then we will be going on to some of the coding assignments. Okay, so the first question is a question about interpolation. So it's like, what is an interpolation process? And the idea here is that how interpolation works is that you have a data for which is defined for a few set, like a function, you can think of it, which is defined for a few set of numbers, and then you want to find out what is the value of the function for a number which is, or for an argument which is not available among the set of your data points. But given that this function is a smooth function between all of these data points where it is defined, you can use an interpolation technique to find out the value of that function in at a point where it is not defined. Right, so this is kind of the basic idea. So it is so in that logic, the right answer to this first question is that the interpolation is the process for finding the value of a function between just 2 points on a curve. And one of the ways to find out such interpolation is the Lagrange, using Lagrange polynomials. And here the question is that you have a function that passes through 2 data points, and then what is the Lagrange polynomial through this. So since you have just 2 points, then the order of your Lagrange polynomial is a linear function. It's of like order 1, and therefore your interpolating polynomial is will have only 1 power of x, right? And so this is kind of the idea. And so now let's find out of these options what would be the correct expression for the Lagrange polynomial which can interpolate between these functions. So for that, let me go to Paint, where I will be using this to demonstrate workings. Okay, so I hope you can see the screen. So the idea here is that imagine that you have a function here and you have 2 points, right? So this is your x-axis and this is the y-axis for that function. And so these points, let me draw it better. So this is A and this is B, right? And in these points, your function is defined as some quantity which is f of A, and then something like an f of B. So let's look at how you will get to have this function. As I was saying, that this is the function that just passes through 2 points, and because of which the Lagrange interpolation should be a straight line. And for the case of a linear function, it's very simple. So you know that and some other any other random point, the function value is x, right? So this is f of x for any other value, and here the value is x. But since this passes just through 2 points, then any line which is passing through points is obviously a straight line, and therefore your function is, as I was saying, is linear. So let's find out the slope of this. So the slope of this function would be like at value of x, its value is y. So you can do something like an fx, which is y, minus f of b, right, by x minus b, and this must equal f8 minus fb And we will come to a more generalized form of Lagrange polynomials later on as we go through the later questions. So this is A minus B. So for any arbitrary point, the slope which is fx minus fb by x minus b must equal to the slope defined using the 2 points where the function is the value of the function is known. Right. So this is kind of the way this Lagrange interpolation would work. And now you can just rearrange these terms together, right? So if you want to do that, so the way to do this is just to make, since you want to find out fx, what's the value given of f given that value of x. So let's make fx a subject of the formula. So for that, what we will have is something like fx, right? And this will be, so you multiply x minus b in here, so this will be fb plus x minus b over a minus b, and this must be multiplied with something like fa minus fb. Right. So this is the thing that you have to do, and once you get this, you rearrange these terms again. And so first you just collect all the terms with fa, and then you collect all the terms with fb. So if you collect all the terms with fa, then it's simple. Only this is the one where you have something like x minus b over a minus b times fa. And along with that, you'll have the rest of it, which is will be collected in FB. So then that would be, because of this, it is 1, and because of the other one, it's minus of x minus b over a minus b, right? And after that, the one that's remaining is FB, right? So all I'm doing is collecting terms of similar type. And now we will take the lowest common multiple in here and just collect the terms together. So then this will give you something like this term will remain with FA will remain the same. And here you'll have something like a minus b and minus x plus b, right? So you will have something like x minus a and a minus b fb, right? And now what you can do is you can rearrange the denominator in here, but by just changing the sign. So if you, and now if you do that, what you will get at the end, sorry, I missed the fa in here. So then what you will have is very simple. You will have something like x minus b by a minus b times fa, and the plus, because we are changing the sign in here, so that will become plus. So you'll have x minus a by over b minus a times f b. Well, this is the kind of the idea of how we'll get it, and therefore, and this is nothing but fx. And so let's write that. So given therefore a function which is defined at 2 points a and b, fa and fb are defined, and then you want to find out the value of x. This is kind of the Lagrange interpolated function that I will be using for interpolating. And let's see when which matches this. So as you can see, it's the option D which matches x minus b by a minus b. So you see x minus b over a minus b times fa. So that's exactly what we are getting in here. Let me get this for becomes easy to follow. So you see fx equals to x minus b by a minus b times fa plus x minus a by b minus a times fb. So that's kind of the idea. Excuse me for my very bad handwriting, but I hope you can follow what I was saying in here. Okay, so now let's move on to the next question, and if there are any doubt at this point, then please feel free to ask me. I will be happy to go over them. Oops, yep. Okay. Check the chat. If there are any doubts, then you can also put it on the chat, or you can just unmute yourself and ask whatever is convenient to you, and I'll be happy to answer. Okay, since there are, I don't see any questions, so I'll just move on to the next one, where it is said that a Lagrange polynomial passes through 3 data points, and therefore now what you're asked is that these are the data points which is given, like the values of x and the values of fx, and now you're asked to find out the value of x at x equals to 7. So let's just to recap what do we mean by Lagrange polynomials. I'm just opening this mathematical article where the general form of a Lagrange polynomial is given, where you see these values px equals to is your Lagrange polynomial, and x1, x2, x3, these are the data points where your values are defined, and so along the x-axis the data points are x1, x2, x3, and goes till xn, and the corresponding value of the function are y's. So you have the y1, y2, and it goes to yn. So all these pairs of x and y's are defined, which are your data points, and you want to make a polynomial approximation to this. And as you can see in here, like this would be an nth order polynomial, depending upon how many data points you have for doing this Lagrange interpolation. And here this is specifically in this specific question we have 3 points, so this corresponds to equation 4, where there's the 3 points are used, and this is and the equation 3 is like a general for n number of points. So just for you to follow, I will also put the link of this page in my chat box, and you can I think you have also gone through the lectures of this week session where some of this has also been discussed. And one thing to note in here, which is not mentioned in any of these in this article, is that this expression that you see to the left of every y's, so this thing which is a large factor in the numerator, factor of different terms in the numerator, and then a product of different terms in the denominator, this entire fraction that you see is defined as L. So the first one is L1, then the second is L2, and the third is L3, and then so on till Ln. So the general form would be then conveniently written as L1 y1 plus L2 y2, and goes and the summation goes to Ln y. Okay, so this is the general idea. So let's now just quickly move on to the question, and let's try to solve it. So that here you see that there are 3 points which is defined, and where the Lagrange polynomial is basically defined. So let me also open up a notepad where I can also do something like this, so which will be helpful for me to type things, and hopefully the size of the text is also pretty much visible. So the idea here is that since we have 3 numbers, so this will go as x minus, so we'll start with the first number, so we'll not have that, so we will have x minus x2 and x minus x3, right? And that has to be divided by x1 minus x2, and this has to be again multiplied. So this the first two, these two are the 2 terms in the numerator. So let me also have one more bracket in here, right? So we'll be then using this up in code, and then we will have something like an x1 minus x2 times x1 minus x3, right? And this entire thing is the factor. This is L1 if you wish, and after this you multiply this with y1. Right. Similarly, we will be doing the same thing, but just with different terms. So now we want to make the base on x2. So you will have x1 and x3, and then you will have x2 minus x1 and x2 minus x3, and this will be multiplied with y2. And then again, we move on to the final expression where we will be basing it on x3. So we will have x minus x3, and so this is based on x3. So we will leave out x3 in here, and we will have something like an x minus, let's do it in ascending order, indices x minus x1 times x minus x2, and then we will have something like an x3 minus x1 and x3 minus of x2 times, at the end we will have y3, right? So this is generally the idea. And now the thing is, I'll just copy this entire thing, right? And let's write a brief, very small C code, which is going to make this calculation. So let's move on. And this, as you are all familiar by this week, this is the kind of the general C code that we have, hello world code, and here we will be defining the values of x. So let's do this. And now the idea is this is a double, or we can use float in fact. So float y val is this, and now it's up to us to define what are the x1s and the things like these, which will be the functions, right? So let's define those. We'll have something like x1 equals something, y1 equals something, and therefore now we are going to define those. And the idea is we want to find this at 7.0, right? And similarly, we will have to also define the y's. So let's do that. So let's go back. I'll have this put in like this, and then I'll have, let's see, this that it's easy for me to write the things. So let's do this. So let's define x and y, x1, y1 first. So your x1 will be 5, and your y1 should be 15.35. And y2. And the last pair. Something like a 15, and this is 3.74. Let's get rid of this redundant line, and we want to find out this. And let's print this then. Print y equals percentage f y underscore, right, times the v. So this is it, I guess, and I'll go to the end and give in line brush, which I have missed. So I have also missed putting in the star in here. So let's break this down then, something like this. Right, so you can see all these polynomials, and I just have to put in the stars just to, which I have missed it previously. So you have x minus x2, x minus x3, and you have x1 minus x2, x1 minus x3, because this is based, this has the basis on x1. Next we move on to basis on x2. So you will have x1 and x3 chosen, and then we move on to basis on x3, where you will have x1 and x2 chosen, right? So we have this. So let's now just run the code. So you see that the value which we have is 13.08, and therefore the right answer you see is 13.08, which is exactly what is required. Okay, now let's look at the next expression, which is about the trapezoidal rule for integration, which asks what is the value for one segment trapezoidal rule up to 4 decimal places. So it just asks for just one trapezoidal, one segment. So the entire integral range of x times e to the power 2x is divided into just one trapezium. And so let's first recap on what is the rule for the trapezoidal integration. The idea here is that you divide your integral, you kind of subdivide your integral space into smaller and smaller trapezoids, and then integrate the area under these trapezoids. So the idea here is, let's take the same example as what we have used for interpolation, but obviously now we are integrating the integral instead of interpolating it. So let's think about that. And now let me go back to the brush where I want to show what do I mean by this. So imagine that these are certain positions where you want to integrate, and this is like okay, so Control Z. So you want to integrate from A to B. This is the function fx that you want to do, and you know the values of the function at every x points. And the idea is that you subdivide this function into smaller and smaller trapeziums. Although the first one is almost like a rectangle, but as you can see, the general shape is a trapezium. Special case of a trapezium, as you all already know, is a rectangle. But as the general shape is a trapezium, you just add the areas of each of these trapeziums, and you assume that the function between any 2 points like this is linear. And therefore, say if you have some function like this, which is extremely wiggly, and then if you want to assume something like a trapezium, then obviously this is not a good choice, right? And this is because if you join these two lines, as you can see in here, assuming that this is linear, then you are overshooting here in this region, you are overshooting, and while in the other region, so let me mark it in a different color, like this one, you are undershooting. And what this is resulting in is that you are getting values which are not exactly accurate. Therefore, in a trapezoidal method, if you want to get values which are accurate, you have to divide the space into smaller and smaller trapeziums. So imagine like dividing the space into these smaller trapeziums, such that within each of the points where you are dividing, the linear approximation of the function, that it changes linearly, is valid. This is kind of the idea. And obviously, as you can see, my drawing is not that good, so I was not able to draw perfect vertical lines, but the idea here is that the lines are perfect, only vertical, and you have parallel trapeziums which you add. Okay, so once I have given you the idea of how this is working, let's go to the Wikipedia page on trapezoidal integration and see that. Look at this formula where you see k equals. So I'm highlighting this formula. You can also perhaps see with my cursor that you have a function which goes from A to B, and you want to integrate it from A to B, which is fx dx. And you can represent it as a summation of these area under these trapeziums, and that's defined as you know, the area of a trapezium is height by 2 by times sum of the parallel sides, right? So imagine that you have a trapezium like this, right? So the area of the trapezium will be this value is h, separation, and this value is, say, a. Let's not write it a, just to I do not have any confusion. So this value will be, say, y1, and this value is y2. So then the area of this trapezium would be something like h by 2 times sum of its parallel sides, y1 plus y2. And you can motivate this from the areas of triangles and rectangles, which you can divide this trapezium into. And the general case in here is that your base is flat. So the kind of trapeziums which we are interested in is actually, although the formula remains the same, doesn't look like this, or rather I would say that it looks like a flat thing. So I would say let's brush. The trapezium which we are looking at will be looking like this, right? And then we will get rid of the other portions, for example. This kind of ways you can do that. trapezium which we are interested in, and obviously this value exactly is y2, right? So once this done, we will be putting in the values in here for our specific case. In our specific case, you see, let's find out what are the values. Here our n is this uppercase n is 1 because there's one zone trapezium. So this value will be the leftmost and the rightmost value. So this will be f of a and f of b, right? So let's write it down in Notepad once again. So for us, and we have only two extremes, all right? So this is that, so it will be 0.5 because of that half thing that you see here times the size of it. So our size is from A to B, so it's nothing but B minus A, all right? So this is B minus A, and this times we have to find out what is F A plus f of this kind of the value which we want to evaluate, right? So let's take this in and put it in VS Code for us, and let's define a function float f, and this will take in a value of x, all right? And let's define our function. Our function is nothing but, I think, let's go back and see what was our function. So it's x times e to the power of 2x. So you have, for this you obviously need math. X times ext of 2 times x is the function which we are looking at. And let's define a. So we start from 0, right? And we go till 1.5. Value which we go till, and now let's give something like float of h. So we know h is nothing but b minus a, so we'll do b minus a. So now let's find out I. So the float I is, I'm just going to copy this, and instead of b minus a, just for simplicity I will put in h, and a and b's are defined. So this is kind of the value of I which we are expecting, and then just we will print. Right, so hopefully everything ticks out. So let's just run this. And here you see 22.60. Let's have it for a few more decimal places, 4 decimal places, say. Uh, 5962, right? And so let's go in here, and you see the correct answer is 22.5962. So this is kind of the thing that we are expecting, and the idea here is that it's just one segment trapezium, so you just have one trapezium for the entire area under the triangle. So you see the accuracy of the trapezoidal rule increases when, obviously there is already what I have discussed, when the number of segments is increased. So if you increase the number of segments, then the linear interpolation which is involved in this trapezoidal rule, which assumes that the function changes linearly between every interval over which you are integrating, is an accurate representation of your function, and your integral converges to the correct value. So if you have question at this point, please ask right now, either by unmuting yourself or just putting it on the chat. I'll wait for like a few minutes. Okay, assuming that since there are no questions, I can move on to the next one, where you see that it's been asked to find out the solution to the following differential equation using the Runge-Kutta method. And here you see we are using the Runge-Kutta method with this step size which is given, and the function, the differential equation, is also given. So we are using this for differential equation, and its initial condition, which is the value at y equals to y, value of y at x equals to 0, is also given. So we are going to solve this with some step size, and we are being asked to find out the value of y at x equals to 0.2. So it's just one step size away from where we are starting. So we are starting at 0, and we are asked to find out the value of y at 0.2. So let me just briefly recap you through how this Runge-Kutta method works. The way this Runge-Kutta method works is that you start with some initial condition, which here in this specific case, as you can see, let me zoom in, it's referred to as t0, and this is h. So this is your step size where you want to find out, according to the differential equation, what will be the solution at that next point in the function. So the idea here is you first go to a place which is midway between t0 and t0 plus h. So there is that distance h by 2, and there you try to approximate the slope of the function. So you approximate the slope of y, and depending upon how many orders of Runge-Kutta method that you do. So this is, for example, RK4. In RK4 you do this is the fourth order Runge-Kutta method. There can be RK2 method as well. So depending on like how many steps that you want to go, you will have a better and better approximation of the slope of your function. And then the idea is that sitting at h by 2, you find the slopes k2 and k3. And after you have found out the slopes k2 and k3, you find out the next slope k4 at the place where you want to know the location or the value of your differential equation after solving it. And there, then you update your function by the slope that you have found out, which is k4. So with that, given that the value of the function is known at t0, which is your initial condition, you can find out the value of the function at th. And obviously, choosing a smaller and smaller value for h gives you a better and better result, generally speaking, in case of Runge-Kutta method. And this is an explicit method in which you solve ODEs. There can be also implicit methods, and depending on something called stiffness of the problem. So I'm not going into too much details of it, and just sticking to the special case of Runge-Kutta method, which has been asked in this specific question. But if just a food for thought, and if you are also interested in exploring this further, there can be two different kinds or types of numerical methods depending on the stiffness of your differential equation, and then these lead to two kinds of solution strategies. One is called implicit, and the other is called explicit. And Runge-Kutta is kind of an explicit method for solving ODEs. So enough of this background. So let's just quickly jump into the problem. As you can see, this is the differential equation, but how things are defined in case of Runge-Kutta is that you'll have something like dy dx or dy dt. So what we are going to do is that to recast this so that we only have dy dx, or the differential in here, and then the rest of it on the other side of the equation. So let's rewrite this in that form. So let me get rid of all of these which I was using previously, and put this in here, put the rest in here. So let's see. So we have 5. So a brush 5. X. Right. So this is the thing. So we will be rearranging this. So with rearrangement, this will be something like dy dx, and this is nothing but 1/5 of cos of x minus x times y cubed. So this is the function. f of xy that we want to find out, right? So let's write this up in VS Code in C. So let's now have a function which is both float is a function of both x and y, and what we are going to return is, remember the decimal points in here, otherwise you will get something like 0, because that is treated in C as integers, which give you, when you divide integers and which is less than, when it's between 0 and 1, you'll get something like 0. So remember to put in this point, which some people forget when they're new. And cos x minus x times y cubed, right? So we'll do something like a y comma 3. So this is how. You can also do something like f y times y times y. Both works. Whatever you find preferred. So here we have defined f, and now let's find out y naught, right? So h is, let's see, I have forgotten. Go back to the question of where it does. So h is 0.2 and y naught is 3, right? So h is 0.2 and h0 is 0, and then 1 is then x plus h, which is where we want to find out, right? So x0 plus h is where your x1 is, and these will be floats. So let me put in. So this is done, which is, this is the place where we want to find out, and we have to want to find out y. This is the initial condition, and let's see, I have forgotten again what's the initial condition on y. So it's 3. Y0 is the initial condition, and now we are going to solve it. And for solving it, we have to define k1, which is x0 y0, and then k2, and k3 is then this, and then k4 is this, right? And then I is basically your y0 plus this. So this is the standard Runge-Kutta fourth order solution. I can just briefly open this up for you so that it's easy for you to also just cross verify what I have done. So let me open up again the Wikipedia article on Runge-Kutta method, and here you see we want to find out the value of y at n plus 1. So the at n plus 1 for us is at x0 plus h. So we start with finding out the values of k. These are the slopes with which we want to approximate the solution. So you start with k1, where the x, so you t in this Wikipedia article corresponds to x in here. So we find out at x0 y0, where we start with, and then we find out at x0 plus h by 2, right? And y at y0 plus h times k1 by 2, and similarly k3 is x0 plus h by 2 and y0 plus h times k2 over 2, and similarly k4 is x1 and y value is y0 plus h times k3, right? And since once all of this is done, we have the values of the 4 values of k's. We are now have to combining these all 4 values. This is again a trapezoidal rule for this combination. You can convince yourself by looking at the slopes of how this is done, and with that you can see that there is a y0, and with that we are adding the different values of k according to the weights that is given by this the Runge-Kutta fourth order method. And finally we are printing this. So okay, this looks fine. So let's just run this code. And you see that the value here is 2.9345. And now let me just go back and verify what's the value that's needed. And you see 2.93 is the accepted answer, and the value which we have got from VS Code is 2.9345. So this is the right answer, which is option B. Okay, So now let's move on to question 7. Here you see what's asked is which of the following cannot be a structure member. So you see that a structure is nothing but a collection of different variables, but it cannot include a function. So that's how C programming language is, that it doesn't allow you to have functions in a structure. And this is what differentiates it from something in C++, where you can have very similar to structure, something called classes, and where you can have functions in it. But in structures, you just can have variables, but not anything other than that. And so the right answer here is that something which is not allowed as a member of a structure is a function. So at this point, I am pausing for a while to take some questions. If any of you have any doubts or anything, then please feel free to ask. Okay, since I do not see any questions in here, I'm straight away moving on to question number 8, where you are asked to match the following. The thing is, what are these different methods? So Newton method is for root finding, and I think we have already discussed root finding last week, which is used to find out the roots of a polynomial, or rather any transcendental equation. And Newton method is one of the ways, one of the numerical techniques to find the roots of such transcendental equations. So the first option is A2. The first match is A2 in here. The next is about Lagrange polynomials, and at the beginning of today's session, we discussed a lot about Lagrange polynomials, and these are used for finding out interpolation of a function. So then B matches with 4, which is interpolation, and then trapezoidal rule. This is also something which we have covered a while ago. This is used for integration, for numerically integrating different functions, and therefore C matches with 1. These are used to find, as we were showing, this is used to find out the definite integral of any function numerically between two intervals A and B, and therefore this is an integration method for evaluating numerical values. Okay, so C matches with 1, and therefore the last one which remains is the Runge-Kutcher method, and just now we have discussed Runge-Kutcher method, and it is used for solving differential equations. So D matches with 3. So then if you look at all these options, then the correct option which has the right matches with every of the options in here is option A, where A2, B4, C1, and D3. Okay, so now let's look at the next question, where you have been asked to find out the value of this function using trapezoidal integration, where we want to divide the region into intervals of 5. So then let's code the trapezoidal integration up, and then we will be using this to using 5 intervals for finding out what's the value of the function, right? So let's go to VS Code, and let me then what I'll do is I'll just undo all the changes and go back to the state where we were written about trapezoidal integration before, and then we will be doing that to find out the numerical value of the integral for this new function. So you see the function is exponential of x times ln of x. So ln of x is nothing but log x, and we have an exponential of x, right? And A is now running from 1 to B is running from 3, and H. So now you see we are dividing into intervals of 5. So now your H is going to be A by 5, because that's the number of intervals that we are using to differentiate this. The idea here is that we find out the function, the values at the two different points. So now for that, we will need a for loop, or right. So you have an A which goes till. So let's have two things which is defined. Just will start with these values. Float. This one. equals to let's type in somewhere else. So let's start with this. So we initially have x1, which is at 8, and now we will do something like is a plus I times h. So this is the value which we are starting with, and 1, 2, 3, 4. And therefore the h is nothing but this b minus a by 5. As you can see, we have already defined it here, so we don't need this. And here we will do I, so this is the integral. So I equals to 0 starts with 0, and then equals f of x1 plus x2, right? Let's go to the Wikipedia article where the things are given. So you have x1 plus x2, and this has to be multiplied with h by 2, right? And then we come out of this. Let's see. I'll just put in one more bracket just to be sure that this is evaluated before anything, and before adding the things, all the things are getting evaluated, and then x1 needs to be then changed. So x1 becomes x2, such that later on you will have the x2 gets updated accordingly, right? And once this is done, we can print the result here. So let's see. I think what I have done in here is I'm getting an error. Let's see what's the error that is happening in here. So okay, so I think what I have done is wanted to get rid of one of the line from the older program, and now this looks fine. So let's just run this. You see, it's 7.3874. So let's just go back. And see what we have done in here. We have got these values, and we have divided into 5 parts, and when we are looking at each of these parts, so we are at x2, which is a plus starts at a, and let's see the function e to the power of x times ln of x, so log x, and we have e to the power of x, 1, 2, 3. Let's I think define this once again. There is something which we have done wrong in here, so let's not have the previous code, and let's try to write this from scratch. This is 3, and n is divided into 5 subintervals, and then your h is this, and then start with A, right? So your A is X is 1 is basically this, and the value of X2 is then I plus 1 times H, right? And your integral should start from I equals to 0 point I this. So this is thing, and then we just print out the value of I, which must be equals to at the end I, and let's print this up outside the for loop. Let's try to run this. No, for some reason this is not running, so let me close VS Code once just to have this restarted and restart my thing. There seems to be some problem. Sorry for the inconvenience that this is causing. Let me just now run things once again. A6A. So now let's run this. So this says the value is 26.12, which obviously we don't match. Here it is written as somewhere between 14.24 and 14.58. So let's see where is it that we are doing this wrong. So we were to find it between 1 to 3, and it's e to the power of x times ln of x. So to understand what's going on, I have already discussed some steps regarding the debugger. So we'll just use the same debugger in here. Okay, so let's look at the local functions. Let's step through. A is 1, then B gets assigned the value of 3, and you can see H, which gets assigned the value of 0.4. So you see that between 1 and 3, if you have 0.4 times 5, so you'll have n steps were 5, right? So you would expect something like 2 over 5. So everything step size is of 0.4. So I think this is right. And then with this, we are going to the next step, and here I is 0. So x1 is 1, and x2 is then everything is 0.4. So then it will be 1.4, as you can see in here. And then we do something like h by 2 f of x1 plus f of x2, and this is then the new value of I. We go back, find out the two values once again, and then add it. So this is the second iteration, and we go here, find out. I think what we are doing is perhaps overshooting this. So this is now I equals to 3. Now for I equals to 4, we will have two values. You see, this is the last one which we should do, and now what we are doing is we are going back and doing one more interval, so which is not needed. So we will just do less than n, because we are doing less than equals to n, which is an additional thing which we were adding. So that's where we were going wrong. So once we fix this error, let's now try to run this code once again. And you can see the value is 14.373627. And now let's see, it's the between as you can see, it was between 14.24 and 14.58. So as you can see, we have correctly debugged the issue, and it was because of this less than or equals to, we are overshooting it, and now the code looks nice in the sense that it correctly ends at the beginning. A and B's are now the correct values. So at this point, if you have any questions, then please feel free to ask. Okay. Okay, then let's move on to the final MCQ, I guess, this one, and then we will cover some of the coding assignments. So in the final MCQ, what you have been asked is to find out, this is a recursion function, and we have already dealt with a lot of recursion functions in one of the previous weeks. And this is one such recursion function, and you have been asked to find out the output of this function. So let's look at what's happening, where the function is called. It takes two arguments, and it is called with the argument 513 and 2. So what's happening in here is that for any value of n which is greater than 0, the function is returning. What the function is doing is it's first finding out the modulus of dividing n with r, and or by modulus what is meant is the remainder. So remainder of the division of n with r is taken, and then that is added to and then with this remainder, what's added is again a call to the same function, but now with a value of n by r and r. So n by r is now checked whether it is divisible or not with r. If it is not divisible, then that the remainder is then again taken in, and then again added with a self call to n by r, and then again check with r, and this keeps on going. And as you can see, the value of n, when you divide it, keep on dividing it by r, decreases. And because of this, as the value of n keeps on decreasing in here, you will have a function where you just keep on adding the remainders, and when it becomes less than or equals to 0, the function stops, and your recursion ends, and then the function returns 0. So let's try this case which is asked in here, which is 503 and 13 and 12. So as you can see, 513 is an odd number. So when you divide it by 2, you leave a remainder of 1. So in the first iteration, you have 1 plus, and after that, so let me open up Paint for you once again. So this is going to make things clear, I believe. So in the first thing what you do is 513 modulo 2. So this is nothing but 1, and so you do something like 1 plus. So 513 by 2 is it leaves a remainder, but you just do a division, and these are kind of numbers which are integers. So what you will get is something like 2, 5, 6, right? Because if you divide it by this, you'll have 256. So you have something like 256, comma 2 is a function that's been passed here, right? So this is f. This is the function, right? So now you again divide it by 2, so you will have 1 plus 2, 5, 6 modulo 2, and then you add f and you divide 256, so you'll have a 128, 2, right? And this goes on. And you'll do it unless, as you can see, n is decreasing unless the value of n is 0. So before the value of n is 0, the final one.
Oh, okay.
So
and
this modulo, as you can see, it is an even number, so this is going to give you 0. So this value is nothing but 0, and you keep on adding zeros unless you go to something like the final one, where you have 1, 2, right? So now here, when you divide 1 by 2, the modulus of that operation is nothing but 1. So you will have 1 from the very first operation, right? And you will have 1 from the second last operation. And then when you divide 1 by 2, and it's an integer division, what you are left with is 0. So in the last iteration, you see you come out of your recursion because your n now becomes less than 0, or rather equals to 0, and then you go to the else statement and you return 0. So all you are doing at the end of it is just adding 2 ones, so the output of this function is 2. I hope this was clear. This question was a little bit tricky, I must admit, and make sure that you understand this. And if you now have any questions, then please feel free to ask. Right. So, yeah, if you're typing something, please feel free. Okay. Okay, then I will then quickly move on to the coding assignments for this week, where we will be writing some of the codes for the different interpolation and the integration functions. So let's see, start with the first one, where it's asked to find out the Lagrange interpolation, given that there are these 5 values in which the function is defined. So 1, 2, 3, 4, 5. See, these are the 5 values where your function is defined, and using these 5 values, you want to make the Lagrange interpolation. So this is done for 5 values. So let's move on and define, right, and we'll take in 5 values in here. X1, X3, X4, right, and obviously launch, and with this we will also take in the value of X. So now let's do this, and now we'll just return. So we'll take the terms. You see how this happens. So we start with basing it with 1, right? So you'll have something like an x minus x2, x minus x3, x minus x4, x minus xy, and this divided by x1 minus x2, x1 minus x3, x1 minus x3, x1 minus x4, and x1 minus x5, right? So this is the first one, and then the second term, the third term, all these are there, right? And we'll also need to take in the y's, right? So we have only taken in the x. Oops, sorry. We have to take in the y's as well. So let's copy this and have the y's. Let's call this y1, y2, y3, y4, and y5, right? Or more smart things that you can do is you can use arrays in here, but that's I'm leaving it up to you. I have already covered the basics of arrays, and I leave it up to you to use arrays, and you can also use the general form of the Lagrange interpolator following the Wikipedia article, where you can use for loops and you can have any number of data for which you can write the general expression. All these are higher order steps that you can obviously do to improve this function and not have something as monstrous looking as this one, but the basic idea is the same, and I leave it up to you to explore these avenues further. So I'm just giving you pointers which you can explore later on if you're interested, but this will also do the job. This is the bare minimum that you need to do. Then we will have something like all these. So we'll have something like y2, y2, y3, 4, and y5. All these are the values where we want to find this out. Okay, so now let's define the Lagrange interpolation thing. So now here we'll be defining the values of the y's, and we'll be putting this in, and then we want to find out the value of the function, right? So here we will be calling Lagrange and the value of x where we want to find out, and this will be the value of y of the function, and so y is equals to, and so something. So now let's once the base of the function is ready, let's put in the values. So it's let's see, it's 10, 22. So we have something like 22. Then we will have something like 15. .0. And now let's set the y's. So we'll have 22.0, and we'll have something like 26.0, 35.0, 48, and 68. Let's put those two in as well. As these are put in, now we want to find out the value of the variable, at different values. So the test cases are trying it as at 4, 5, and 2. So let's then do that at 4. So now let's try to run the code. (10, 22, 15, 26, 18, 35, 22 is 48, and 30 is 68, and what we want to find out is the value at 4, right? And let's see. So we have used the value at 4, and then we are calling branch with x1, x2, x1, x2, x3, x4, x5, and y1, y2, y3, y4, y5, and then x is this. Right. So let's look at this is like x minus x2, x minus x3, x minus x4, x minus x5, and this multiplied by x1 minus x2, x1 minus x3, x1 minus x4, x1 minus x5 times by 1. I think this is fine. So the same thing is done in here. So this gives me a value which doesn't make sense to me, because you see the function is kind of increasing, but what I get in here is a function which doesn't seem to is very large value. So at 4, since this is like at values of x, you see the value of y which is increasing, and then and this keeps on increasing, and unless you have some value which is which starts with 10 and the value is 22, so something which is at 4 should have given you some value which is lower, but we don't get that. So I'm just trying to figure out what is it that we are doing wrong in here, so that we can debug the code. So let's first verify that we have put in the correct numbers or not. X2, so we have 10, 15, 18, 20, 30, 10, 15, 18, 20, 30, as you can see here, and then we have 20, 26, 35, 48, and 68. Okay. Velocity of the car at different instance, so 2, 0. B is 41.62, and then this is okay. I think what it's done in here is asked for 20, not at 4. So okay, let's run the test case where we look for a value of 20. 141.8, 41.62. So I think this is not making sense at all. And this is 25 and 16. $15, 26, 18, 35, and 22, 48, and 30 is 68, right? And then this has been used to find out the value of the function, right? So let's try to break it down into the different values in here. Oh, sorry, I got it. What I've done is I have forgotten to pass the value of x. This was a really silly error, which I think I did. I was passing some different value of x, which was giving me the error. So the value of x needs to be passed properly. So I was passing a different value, and now I think this should be working fine. Let's see. Yes, at f equals to 20, the value of the function is 41.6. So now let's go in here. Yes, you see that at 20, its value is 41.62. So since we are putting it in just 2 decimal places, so let's do that as well. So this just puts it in 2 decimal places. And let's run this code. So the thing what I was doing is I was forgetting to pass the variable properly. Okay, so let's then go through the other test cases. So I have something like 20, which gives me 41.62, and then after that, let's use the 25 value. Run the code once again, and I have 56.42. So let's again verify 56.42. This is matching, and then finally we have something like a 16. So let's run this. And here we have 28.74, and you see 28.74. So this matches perfectly. So the thing which was problematic is I was not passing the right value of x. This was fixed to some other value, and this was although the interpolation function was right, it was not called to the value that we want, and that's why we were getting a different result from what was expected. And once that is fixed, you see that this is working very well. I leave it up to you to kind of use arrays and write the general function, and that would include this, coding this up, which is equation 2, as you can see, which is a product of x minus xk times xj minus xk, where k is the factors which runs from 1 to all of your values, and where k not equals to j. So this you can use a for loop to code this up, and you can use arrays for a general function, which I leave it up to you to do it. Okay. So since we are done with this, which was first one, we will be using trapezoidal rule to integrate with 10 segments to integrate between a and b with the values of a and b taken from the test cases. So it's x squared dx, and we exactly know actually the value of this integral analytically, and so this is a good test to see how well the trapezoidal integration works. And so let's now go back, and I'll undo this because we have already written a trapezoidal integration code a while ago. I think we can use that, and we'll just change the function in here to the function, new function, which is asked in here. And oops, sorry, I'll just change the thing. Let's see, where was this? Okay. So I'll change the new function in here, and here you can see what's asked is integrating it from a to b x squared dx. So this is now very simple. This is just how of x comma 2 is x squared, and we integrate it from a to b. So we'll be choosing a, which is 1 and minus 2, or I think a and b. So it's a is minus 2, b is 1. You can also take these as inputs from the user, but for now I'm just keeping these things simple. And then you have 10 segments in here. So n is 10. That's all you want. And then h has been set. Your I is also set, and you just then print I, right? So let's run this. And you can see the first one is 3.045. So this is exactly what we are matching in here. And now we are going to change a and b's to new values, which corresponds to the next test case, which is between 0 and 1. So let's compile and run this code again, and say fair enough, you have something like 0.335500, and the last one, which is between 1 and 3. So it's 1 and 3. And let's run this, and we have something like an 8.68, which matches. So you see that this trapezoidal integration is working fine, and we have already discussed the code of how this is working. If you remember, when we were first writing this code, while doing the MCQ questions, we put in wrongly a equals, which was just overshooting the value. So make sure this is less than n, and then this is what works very well. So let's move on to the last assignment of this week, assignment 3, because the final assignment, which has been asked to use recursion to reverse string. This has already been covered in one of the previous week session. So I would ask you to go back to that previous week session to look at how we are using recursion to reverse an input word, and this is exactly the same thing which has been asked in this week as well. So I'm not going through that and repeating it. The video has been recorded and it's on YouTube, so you can check it out. If you have doubt at that point of time, then I can come back I will be next week, or there will be an extra session which I will be taking right about at the same time at 3 o'clock in the afternoon tomorrow as well. So stay tuned for that, where I'll be also covering any of the doubts which any of the people will be having over the entire program of 12 weeks of this NPTEL session, where you can also ask questions that you might be having. So have a look at that, and if you find any doubt on this recursion to reversing string to recursion, then I'll come back to that tomorrow. Otherwise, let's go dive straight ahead to the final question, where you have been asked to use recursion to find if a number is prime or not, right? So let's do that. So for this, what we would need is something like a function which we will be calling is prime. But before doing that, there is a specific requirement, and the requirement is that we want the function to be using recursion. So the way this would work is that we will keep on dividing something by 2, right? This is something called, I think if I remember correctly, School's method, where what you do is that you keep on dividing a number by all the values starting from like 2 to a value which is root n, and if any of the numbers from starting from 2 to root n divides the number that you are divides the number n, then you will know that this is not a prime number. But if none of the values from starting from 2 to root n is able to divide your number, then you know that this is a prime number. This is one of the simplest way to do this is using for loops, but since we are using recursion, and we will keep on increasing the value of I, which we are going to divide a number by, and check for the modulus. So that's the idea, and we will start with 2. So okay, so for that I'll also use something called a structure. This is just because there were structs which were covered in previously, so I'll use the similar concept. So I'll call this f(args). So this will be the argument. So that there will be 2 things that we'll be having in here. One is that number n, and the other is the number I. So you divide n by I, and you see the modulus of that operation, and if this is modulus is 0, then you will know that the function is the number n is actually a prime number. Otherwise it's not, provided that you have exhausted all the sets. Now we will use a function like which will give you an int. So this int is like a prime function. We'll call it var prime. So this will take in something like this is going to take in the argument which is in. So this is the input argument that this function is going to take, right? And we will call int n is equals to in.n. So this accesses the n element of it, and then int I equals to in.I question mark in.I else to. So what this means is that we will check for in.I, and if no value of, so if some value of in.I is given, then that will be assigned to I. If no value of in.I is given, then the default value is 2. So then what this means is that it is going to assign the value of 2. So this gives you a starting value. and then we are going to look at something like if n is less than or equals to 1, then we are going to return 0. If it is 0 means it's not prime, while 1 means it's prime. If n is equals to 2, then we say that it's prime, because by definition 2 is an even prime number. And after this, we do a percentage. So this is the modulus operation. And when we say that if it is a modulus operation, then obviously it's not a prime number because it's divisible. Because after doing a modulus operation, if you get something, if you get a 0, then you know that this number is obviously not a prime number. And then if you go I times I, so this is I square. So if I square is greater than n, then that would mean that you have gone beyond root n, right? And once you see that you have gone beyond root n, then you have exhausted all your space, because you will be calling this with n plus 1, n plus 2, n plus 3, something like that. And since and this I is going to increase, so n plus I is what you are going to call it. And if you go till I square, and you know, then you know that none of the previous i's were able to divide the function and get a remainder which is 0. So none of the i's were divisible, and therefore you have come to the conclusion that this is a prime number. And then you call f args, and you call it next. So this is the next one that you would need. Sorry. Next one that you need, and you call it with n comma I plus 1, because this is the next argument, where the next structure that I define in here, and then I'll call var prime next. So what this is going to do is now call it with the next structure, which is next. So next struct, which is of the type f args, and then this is called with the value next, and then this next value is going to be like we start from 2, and then this is going to 3, 4, and then all the numbers are then checked till root n, basically. And now, since we want to wrap it up in terms of just one function, which is like which I'm going to call it is prime, right? Because that's what we are going to call. So I'll just call it is underscore prime, and this I will be using 3 dots. So this means some arguments that I'm going to pass, and then this has to go to var prime, and this is has to go to f args, and we are using something called v args. So what this would mean is that I can put in variable arguments, because you see that except for all the calls to this internal function where I is 2, the I is automatically determined. So this is the is prime thing. Okay, so now I'm just going to take in int n, some value I'm going to take in, and now I'm going to check int result is equals to, sorry, this is result, and I'm going to take count this, and I'll just call it is prime n. So now what this does is it's just checks whether the number is prime or not. So if it is prime, it gives you 1, and if it is not prime, then it gives you 0, right? So now this thing is simple. What I do is %d, the number is prime, then I call yes, otherwise I call no, right? So is %n is the number that I say is prime, then it's yes. If it's not prime, then I say it's no. So this is the ternary operator which I'm using, which I'm comparing result with, right? So once this is done, I come out of the int. So this is this line. The only line which I find is difficult to understand a little bit is the line in here, which is line number 19, where I use something like some C macro, which is called this variable arguments, which just helps me to pass different number of arguments, because in general you have to pass both n and I, but that is only done from function calls, which is inside to var prime. Otherwise, we are just calling is prime with just one value. So that's why this packing is done, and all this is because C doesn't support default values for some kind of arguments which you are passing, which is 2. But anyways, this is kind of something which I would encourage you to please go and check. Since we are at week 11, which is fairly advanced in terms of C programming, So I thought I would just give you a flavor of also some kind of advanced topics in this field. So let's try to run this now. And it's 7 prime. The answer is yes. So now we are going to check all of these like 51, 29, 13, and 40. So let's check this. Okay, so let's now take result n from the user. So that can also be done. So let's first find do a printf, enter a number, and we are going to give and the scan. So now this is going to just check it together, and this is before this. Okay, so now let's check this. So 51. So is 51 prime? The answer is no. Let's check the next thing. So 29 is 29 prime. The answer is yes. It's 13 and 40 are the two other things that we are going to check. Is 13 prime. The answer is again yes. And the last one, which we are going to check, is 40. So is 40 a prime number? The answer is no. So 40 is obviously not a prime number. So I hope this, as you can see, this is kind of working very well, and I hope this answers all the doubts that you might be having related to the different numerical techniques that were covered in this penultimate week of this NPTEL session. And I hope you have also enjoyed learning all the different numerical methods, and you will be able to apply this to not only answer the questions which will be asked in this week and also in your exams, but also in future in whatever work you are doing. And I hope that now you're well equipped and confident enough also to code this up in C, and you will be interested in exploring the different aspects which I also told you over the course of today's discussion in future. And on that note, I'm thanking you all for your time, and thank you all for listening to me. And again, if you have any doubt, please feel free to contact me anytime. I will be happy to address your concerns and questions. So on that note, I thank you all for listening, and I will now then end the session in here, and we will meet tomorrow, where I'm going to have an extra session at around 3, where I'm going to cover some of the doubts which you might be having. And on that note, bye for now, and have a nice weekend. And I'll just stop sharing my screen, stop the screen share.